What is the largest thing in the universe? For centuries, that question has captivated astronomers, philosophers, and storytellers alike. From the planets of our solar system to the majestic spirals of galaxies, and beyond to the vast cityscapes of galaxy clusters, our understanding of cosmic scale has expanded with every discovery. Each time we thought we had found the boundary, the universe revealed something even grander. But the largest structure of all is not what most people would expect. It is not a massive star or a sprawling galaxy cluster. In fact, it is not even made of matter. The largest thing in the known universe is nothing, or more precisely, the cosmic void. These immense regions of near total emptiness stretch across billions of light years and hold the power to reshape our understanding of the cosmos. They are not black holes, nor are they mere gaps between galaxies. They are the very framework that defines where galaxies can exist. In this journey, we will explore the breathtaking structures of the universe, from glowing superclusters to the haunting abyss of the voids, and uncover the strange truth that the universe may be built not of presence, but of absence. Imagine standing on a mountaintop, gazing at a glowing city in the night, its lights flickering in patterns of streets and neighborhoods. Now lift that image and place it in the cosmos. That is what a supercluster looks like. A cosmic city made not of buildings and roads, but of galaxies and dark matter. These structures are the largest gatherings of galaxies ever observed. Immense regions of space where hundreds of thousands of galaxies are drawn together by the invisible force of gravity. Superclusters do not form tidy spheres or uniform clumps. Instead, they stretch across hundreds of millions of light years, forming tangled threads, twisted branches, and sheets of galactic material. They are the busiest crossroads of the universe, places where the cosmic web converges into dense nodes of activity. The shapes they form are almost biological in nature, interconnected, branching, alive in their complexity. The smallest superclusters span at least several hundred million light years. The largest can stretch across 10 billion light years, a scale nearly beyond human comprehension. Our own galaxy, the Milky Way, is not isolated in the cosmos. It lives in a small group of neighboring galaxies, known as the local group. This group itself is embedded within a larger structure known as the Virgo supercluster, which contains dozens of such groups. But in recent years, astronomers have realized that even the Virgo supercluster is only a branch of something far larger, a sprawling supercluster called Laniakea, a Hawaiian word meaning immense heaven. Laniakea is a cosmic metropolis encompassing over 100,000 galaxies across 500 million light-years of space. To put this in perspective, if a single galaxy were the size of a human being, then Laniakea would be the size of a large continent. And each of those galaxies is itself home to hundreds of billions of stars, many with planets, moons, and perhaps even life. That is the scale we are speaking of: cities of galaxies, metropolises of stars. The Milky Way resides on one of Laniakea's outer limbs, not even at its center. We are, in cosmic terms, a distant suburb of an incomprehensibly vast structure. Many superclusters are named after the constellations that astronomers must look through to observe them. The Coma supercluster, the Virgo supercluster, the Hydra Centaurus supercluster. Others bear more creative or dramatic names. In 2022, Japanese scientists discovered one of the most massive superclusters ever observed. They named it Kin-Go-Ra, after a mythical three-headed beast, the nemesis of the legendary Godzilla. Its structure alone contains the mass of over 10 million billion suns. Despite their size and grandeur, superclusters are not permanently bound. While individual galaxies and clusters within them may be held together by gravity, the supercluster as a whole is still expanding. The mutual gravitational pull of all its galaxies is not enough to overcome the accelerating expansion of the universe. Superclusters are like giant cosmic gatherings caught in the act of dispersing, slowly drifting apart over billions of years under the influence of dark energy. Still, superclusters remain among the most majestic structures we have ever observed. They are a testament to the power of gravity and time, pulling matter into complex webs across cosmic distances. The superclusters are not evenly distributed throughout the universe. They cluster themselves, forming even larger patterns, a network of networks, a superstructure of unimaginable scale. This network is what we now call the cosmic web, and superclusters are its glowing nodes. But as immense as superclusters are, they do not dominate the universe. They are stunning, dense, brilliant, but they are also rare. In the vast darkness between them lies something even larger and more mysterious. These are the regions where light fades, galaxies thin out, and the universe becomes eerily quiet. They are not structures of stars, but of silence. They are not bright cities, but cosmic deserts. And though they may appear as nothing, they shape everything. So, while superclusters may be the glittering jewels of the universe, they are not the crown. They are the peaks of mountains, the dots on the map. To truly understand the universe's largest architecture, we must turn our attention to what lies between, the empty spaces, the cosmic voids. For it is in those vast, silent expanses that we will find the true rulers of scale. They are not luminous, they are not full, but they are immense beyond measure, and they are waiting. In the late 1970s, two American astronomers, Laird Thompson and Stephen Gregory, undertook a daunting task. They set up at Kitt Peak Observatory in Arizona, determined to map the distribution of galaxies in the sky. Night after night, they remained at the telescope, manually recording galaxy positions. Their observations were painstaking and precise, and they relied on a rudimentary tool for detection, a photomultiplier tube that allowed them to measure incredibly faint light, a forerunner of the modern digital camera. Their method was not entirely new. Astronomers had been mapping galaxy positions for decades. But Thompson and Gregory introduced two major innovations. The first was technological. using amplified light to peer deeper into space than ever before. The second was conceptual. They visualized their results in an unusual way, plotting the galaxies in a wedge-shaped slice of space, with the Earth at the apex and galaxies expanding outward in a cone. This visual approach made something astonishing immediately apparent. In the direction of the Coma Cluster, a dense collection of galaxies known for many years, they expected to find a bustling spread of galactic structures. But what they found instead was something utterly unexpected: a vast region of space nearly devoid of galaxies. In their plot, the Coma Cluster appeared as a thick cloud of dots surrounded by scattered points. And then, suddenly, a dark, empty patch stretched millions of light-years across, an apparent hole in the universe. They had discovered a void. The reaction from the astronomical community was not warm. Many dismissed their findings as observational error or statistical fluke. Some even accused them of wishful thinking, seeing what they wanted to see. After all, the prevailing view in Western cosmology at the time was that the universe, on large enough scales, was homogeneous. That meant galaxies might clump together here and there, but in the end, matter should be evenly distributed throughout the cosmos. A vast empty region had no place in that picture. But science rarely moves in only one direction. Around the same time, a group of Estonian and Soviet astronomers published results from their own galaxy surveys. Although they did not use the same pizza slice diagram, they too noticed large empty spaces in the sky. In contrast to the skepticism in the West, theorists in the Soviet Union had already anticipated such findings. One of them, Yakov Zeldovich, had proposed that the universe evolved like a sheet of dough, folding and stretching into sheets, filaments, and voids. According to Zeldovich's ideas, matter did not simply spread out evenly over time. Instead, gravity caused matter to collapse into dense structures, leaving behind vast cavities, cosmic voids. In this framework, voids were not errors or blemishes. They were inevitable consequences of how the universe evolved. But it would still take time for the Western scientific community to accept them. That moment arrived in 1981, with a second independent discovery that could not be ignored. A team led by American astronomer Robert Kirshner was conducting a survey in a completely different region of the sky. What they found was even more staggering: a truly colossal void, later named the Boötes Void. This empty region stretched nearly 400 million light-years across. It contained almost no galaxies, no clusters, no filaments. The Boötes Void became the largest known structure in the universe at the time, not because of what it held, but because of what it lacked. The existence of both the Coma Void and the Boötes Void forced a reckoning. Astronomers could no longer claim that voids were statistical artifacts or mere observational quirks. Instead, they began to realize that voids might actually define the architecture of the universe. Galaxies were not scattered randomly like sugar on a table. They clung to threads and sheets, leaving behind gaping holes in the cosmic fabric. The universe was not homogeneous at all, not on any scale that humans could easily imagine. From that point on, the study of large-scale structure in the universe began in earnest. Researchers around the world launched surveys and simulations to uncover the true shape of the cosmos. What emerged was a dramatic new vision of the universe, one not filled uniformly with matter, but rather arranged like a colossal web. Galaxies gathered in clusters. Clusters formed filaments. Filaments wove into walls, and between them all yawned the cosmic voids, stretching like great black oceans between islands of light. This new picture of the universe was not just aesthetically compelling, it was revolutionary. It overturned decades of assumption about cosmic structure. No longer could astronomers rely on simple models of uniformity. The voids demanded explanation. How could such large empty spaces form in a universe where gravity pulls everything together? How could nothingness take on structure and scale? The quest to answer these questions would lead cosmology down bold new paths. The discoveries of the 1970s and 80s reshaped the field. What began as anomalies became cornerstones. Once ignored or even mocked, voids took their rightful place as defining elements of the cosmos. They were not accidental gaps. They were fundamental. The galaxies, bright as they may be, merely trace the walls and edges of deeper truths. And the truth was this: the largest structures in the universe were not made of matter at all. They were made of absence. They were made of void. A void is not merely the space between galaxies. It is not an accidental absence, nor a leftover gap in the cosmic scaffolding. In the language of modern cosmology, a void is a vast region of space where the density of matter is significantly lower than the cosmic average. While most galaxies congregate along thin threads and sprawling walls of the cosmic web, voids are the immense cavities in between, the silent chasms where galaxies are few and far between, and matter itself seems to vanish. To understand a void, imagine taking a cube of space from the universe and measuring the amount of matter inside it. In a typical region, you might find 1 hydrogen atom per cubic meter, a number that already seems staggeringly empty. But inside a cosmic void, the density can drop to less than 20% of that cosmic average. These are places where even a stray hydrogen atom is a rarity. Galaxies, stars, planets, all the brilliant jewels of the cosmos are simply not there. Yet voids are not perfectly empty. They are not vacuums in the classical sense. Within their dark expanses, you can still find wisps of gas, the occasional dwarf galaxy, and the ever-present sea of cosmic background radiation. Neutrinos, cosmic rays, and scattered photons travel freely through these regions. But what defines a void is not complete emptiness. It is relative emptiness. Compared to the bustling hubs of matter that surround them, voids are quiet, still, and hauntingly vast. Voids are not spherical bubbles floating aimlessly in space. They have shape, they have structure. Some are flattened, others elongated, stretched along the invisible threads of dark matter that weave the universe together. Often, multiple voids are connected, forming sprawling basins of low-density space. These voids may grow, evolve, and even merge, forming larger and larger structures. And like the galaxies that gather into clusters, voids themselves form patterns, nested, layered, and sometimes fractal in their complexity. The boundaries of voids are where the universe begins to light up again. These edges are not sharp, like the walls of a cave. Instead, they are gradients, transitions where matter begins to accumulate. Here, faint galaxies become visible. Gas becomes denser. Gravity begins to take hold. These boundaries, called void walls, form the skeleton of the cosmic web, connecting the emptiness within to the luminous clusters and filaments beyond. Voids may appear lifeless, but they give shape to everything. Because they are so empty, voids are also incredibly stable. In the crowded neighborhoods of the universe, galaxies collide, stars are born and destroyed, and black holes consume matter in violent bursts. But inside a void, time flows differently. There is little interaction, little change. Over billions of years, a void will slowly expand, growing in volume as surrounding matter is pulled away. It is not an explosion, not a collapse, but a slow unfolding of silence. For cosmologists, voids are more than just curiosities. They are natural laboratories, regions where the laws of physics play out on a clean, undisturbed canvas. Their simplicity makes them powerful tools for testing theories of gravity, dark energy, and the evolution of cosmic structure. In places where matter has gathered, the physics becomes messy and complex. But in the voids, the universe whispers more clearly, unburdened by the noise of stars and galaxies. In philosophical terms, voids challenge our understanding of existence. We are drawn to what is full: stars, planets, galaxies, life. But it is the emptiness that defines the structure of the cosmos. Without voids, there would be no clusters, no filaments, no shape to the universe at all. The absence of matter gives context to its presence. Just as silence defines music and darkness frames the stars, so too do the voids reveal the architecture of everything that exists. At the points where multiple filaments intersect, we find galaxy clusters, the densest, brightest cities of the universe. Between these clusters, the filaments stretch like the roads that connect them. Surrounding it all are the vast voids, expanses of near emptiness where matter is scarce and galaxies are few. Together, the clusters, filaments, walls, and voids form a latticework that resembles a three-dimensional spiderweb spread across the entire observable cosmos. The cosmic web is not made of string or fibers. It is built from gravity, matter, and time. Galaxies are not scattered evenly throughout the universe. They cling together, pulled by the invisible hand of gravity. Over time, these gatherings form dense clusters, which connect to one another through elongated bridges of matter called filaments. These filaments stretch across hundreds of millions of light years, threading galaxies together like beads on a cosmic string. At the points where multiple filaments intersect, we find galaxy clusters, the densest, brightest cities of the universe. Between these clusters, the filaments stretch like the roads that connect them. Surrounding it all are the vast voids, expanses of near emptiness where matter is scarce and galaxies are few. Together, the clusters, filaments, walls, and voids form a latticework that resembles a three-dimensional spiderweb spread across the entire observable cosmos. This cosmic web is not a product of imagination. It has been revealed through astronomical surveys that map the positions of galaxies in 3 dimensions. Surveys like the Sloan Digital Sky Survey have charted the location of millions of galaxies, revealing the tangled patterns of the universe. When these maps are visualized, they show sweeping arcs, long tendrils, and enormous walls of galaxies, all surrounding the emptiest regions, the voids. The scale of the cosmic web defies human comprehension. Each filament can be hundreds of millions of light years long. Each cluster can contain thousands of galaxies, and each galaxy is home to hundreds of billions of stars. Yet from afar, these monumental structures seem delicate, like strands of silk floating in darkness. The cosmic web is both fragile and immense, elegant and overwhelming. It is the scaffolding upon which the universe is built. But the web is not made of galaxies alone. In fact, what we see is only a faint shadow of the true structure. Beneath the galaxies lies something deeper, dark matter. This mysterious, invisible substance makes up the majority of mass in the universe, and it is dark matter that forms the true skeleton of the cosmic web. Galaxies are drawn to dark matter filaments, like dust gathering along magnetic fields, illuminating the underlying structure. Cosmological simulations, such as the Millennium Simulation and the Flamingo Project, allow us to visualize the evolution of the cosmic web over billions of years. Starting from the early universe, just a few 100,000 years after the Big Bang, we see tiny fluctuations in density grow under gravity's influence. Those small irregularities stretch and condense, forming the first filaments and voids. Over time, the web becomes more intricate, more vast, and more defined. The cosmic web is not just a visual pattern. It is a physical reality that determines how the universe works. It guides the motion of galaxies. It shapes the formation of stars. It even influences the paths of light itself. When light from distant galaxies passes near dense filaments, it bends slightly, an effect known as gravitational lensing. These subtle distortions allow astronomers to map the invisible mass and confirm the existence of the web's dark matter framework. And yet, for all its grandeur, the cosmic web is incredibly thin. Most of space remains empty. The filaments, as massive as they are, take up only a tiny fraction of the universe's volume. The vast majority is void, open, silent, and dark. The web is a pattern of light on a canvas of darkness. Its glow draws our attention, but its emptiness is what defines its shape. Just as the threads of a spiderweb shimmer against the air, so too do galaxies shimmer against the void. In many ways, the cosmic web is like a living system. It grows, it evolves, it stretches and changes over time. Gravity acts like a gardener, pruning and feeding the dense regions while allowing the voids to expand. As the universe ages, the filaments become thinner, the clusters drift apart, and the web stretches across ever greater distances. What we see today is not the final shape, but one moment in a grand unfolding story, a story written in stars and emptiness. And so, to understand the universe, we must understand the cosmic web. It is the great framework of existence, the invisible map that defines where galaxies form and where voids expand. It is not a static structure, but a dynamic and growing one. The web connects all things, from the smallest satellite galaxies to the largest superclusters. It is the fingerprint of the Big Bang, the echo of quantum fluctuations, and the architecture of everything we know. These stretched-out fluctuations created tiny differences in density throughout the early universe. Some regions contained slightly more matter, while others held slightly less. Over time, gravity amplified these differences. Matter flowed toward the denser regions, enhancing their gravitational pull, while the underdense regions, the ones with less matter, began to empty out. This process gave rise to the contrast between clusters and voids, between brilliant galaxies and the darkness in between. These stretched-out fluctuations created tiny differences in density throughout the early universe. Some regions contained slightly more matter, while others held slightly less. Over time, gravity amplified these differences. Matter flowed toward the denser regions, enhancing their gravitational pull, while the underdense regions, the ones with less matter, began to empty out. This process gave rise to the contrast between clusters and voids, between brilliant galaxies and the darkness in between. The universe at that stage was a swirling soup of hydrogen, helium, and dark matter. There were no stars, no galaxies, no structures yet, only temperature fluctuations and density gradients drifting through the expanding cosmos. As gravity gathered matter into clumps, those clumps merged into filaments and eventually ignited the first stars. Meanwhile, the regions that lacked sufficient mass to collapse remained quiet, expanding steadily into the vast emptiness we now call voids. The formation of voids followed a quiet path. Where matter was abundant, gravitational collapse triggered violent processes: galaxy formation, supernova explosions, black hole births. But in the voids, very little happened. They were not torn apart or set ablaze. Instead, they simply grew. As galaxies and clusters pulled more matter toward themselves, the voids were left behind, emptied out, expanded, and deepened by the migration of material away from them. In a universe governed by gravity, the rich get richer. Dense areas grow denser, attracting more material, while sparse areas grow sparser. Voids did not form because something was taken from them. They formed because everything flowed away. Over billions of years, this uneven dance of attraction carved out a cosmic foam, pockets of emptiness enclosed by sheets and filaments of galaxies. The first stars brought light, but the voids brought structure, shaping the negative space of the universe. Void evolution is not static. These regions expand over time. As the universe itself stretches, so too do the voids. Occasionally, two neighboring voids merge. This happens when the thin wall of galaxies that separates them slowly disperses, with matter being pulled toward nearby clusters. Eventually, the distinction between the two voids vanishes, and they become a single, larger void. Unlike galaxy collisions, void mergers are gentle, graceful events, silent expansions rather than cosmic crashes. Because voids grow slowly and without violence, they preserve a kind of memory of the early universe. Unlike galaxies, which are shaped by chaotic events and energetic forces, voids remain relatively untouched. Their evolution is smooth, driven by geometry and gravity, not explosions or feedback. This makes voids uniquely valuable to cosmologists. They act like fossils of structure formation, traces of the primordial conditions that gave rise to the grand cosmic web. To understand the modern size and scale of voids, astronomers use sophisticated simulations. These models start with the known conditions of the early universe and allow the laws of physics to play out over time. From these simulations, we see how small fluctuations expand into vast voids. We can even trace how voids influence the growth of nearby filaments and clusters, shaping the cosmic web through their silent gravitational pull, or rather, through their lack of it. The expansion of voids is also affected by a mysterious force, dark energy. In regions where matter is scarce, the influence of dark energy becomes more noticeable. It acts like a subtle repulsive force, accelerating the expansion of space. Within voids, where gravity is weak and matter is thin, dark energy dominates. It pushes outward, driving galaxies farther apart, thinning the filaments, and allowing voids to grow even more. In this way, the deepest emptiness is also where cosmic acceleration begins. The history of voids is not just the story of what is missing. It is a history of balance, of cosmic tension between presence and absence, matter and emptiness, light and dark. The same forces that pulled the first atoms together to form stars also pushed others away, leaving behind great chasms. Voids are not failures of creation. They are the silent witnesses to it. And in their growth, in their sheer scale and elegance, they reveal a truth. That sometimes what is not there matters just as much as what is. For centuries, astronomers focused on what they could see: planets, stars, galaxies. But measuring what is not there presents a different kind of challenge. Voids, by their very nature, are defined by absence. They are vast regions of low density, but they do not announce themselves with light or motion. Instead, they are discovered through silence, through the gaps in the distribution of galaxies, through the way matter avoids them. Measuring a void is like mapping the invisible. Early surveys revealed the first hints of these empty regions, but it was not until the rise of large-scale galaxy catalogs that scientists could begin to measure voids systematically. Projects like the Sloan Digital Sky Survey mapped millions of galaxies across the sky. When these maps were rendered in 3 dimensions, the voids emerged as ghostly volumes, cavities surrounded by bright walls of galaxies. With each new survey, the catalog of voids expanded, and so did the need for precise methods of classification. But how does one define a void? It is not enough to simply look for empty space. Astronomers needed a consistent method to identify and compare voids across different regions of the universe. The answer came from an unexpected source: geography. In the study of landscapes, scientists use the concept of watersheds, regions where all water flows to the same destination. By imagining galaxies as mountaintops and voids as valleys, cosmologists realized they could borrow this same technique to trace the flow of matter. This approach, known as the watershed algorithm, allows scientists to define the boundaries of a void based on surrounding density. Just as rain flows downhill into the lowest point of a valley, matter flows away from the centers of voids toward the denser filaments and clusters. By tracing these gravitational gradients, cosmologists can outline each void's shape, size, and extent. What was once vague and subjective becomes measurable and objective, grounded in the physics of space and time. Using this watershed technique, researchers have identified tens of thousands of voids in the nearby universe. Some are relatively small, only a few tens of millions of light-years across. Others span hundreds of millions. Each void is tagged and cataloged like a specimen in a cosmic archive, with its position, volume, shape, and surrounding structures recorded for study. These measurements help us test theories of cosmic evolution and constrain the properties of dark matter and dark energy. This realization gave rise to the idea of a fractal hierarchy of voids. In mathematics, a fractal is a shape that repeats itself at different levels of magnification. The cosmic web appears to follow a similar principle. Within every large void, there may be subvoids. Within those, even smaller ones. It is a structure within a structure, echoes of absence cascading through scale. The result is a universe that is not only vast, but deeply layered in its emptiness. This realization gave rise to the idea of a fractal hierarchy of voids. In mathematics, a fractal is a shape that repeats itself at different levels of magnification. The cosmic web appears to follow a similar principle. Within every large void, there may be subvoids. Within those, even smaller ones. It is a structure within a structure, echoes of absence cascading through scale. The result is a universe that is not only vast, but deeply layered in its emptiness. Of course, we cannot observe every level of this hierarchy. The faintest galaxies and smallest filaments are beyond our current reach. But simulations, digital universes run on supercomputers, show this nesting clearly. They suggest that voids are not just emptiness, but dynamic systems with their own internal architecture. These simulations help bridge the gap between theory and observation, allowing us to infer what lies beneath the surface of what appears to be nothing. By combining observational surveys with computational models, cosmologists have created detailed maps of the voids surrounding us. These maps reveal that voids are not scattered randomly, but form a structure of their own. They cluster together, they interact, they evolve. Measuring and classifying them is not just an academic exercise. It is a way of decoding the deep logic of the cosmos, a way of listening to the silence between the stars and translating it into knowledge. In the end, voids remind us that the universe is not only composed of presence, but of pattern. Not only of light, but of space for that light to shine. Measuring a void is more than measuring emptiness. It is measuring possibility, the vast invisible framework that holds galaxies in place and gives shape to existence itself. If voids are the silent deserts of the universe, then supervoids are the great cosmic abysses, vast, sprawling regions of near-nothingness that stretch across hundreds of millions, even billions, of light years. These are not mere gaps between clusters, but entire volumes of the universe where galaxies, gas, and even dark matter become almost absent. They are the largest known features in the observable cosmos, not because of what they contain, but because of what they erase. The Boötes Void was the first true supervoid ever identified. Discovered in the early 1980s, it was so large, so shockingly empty, that it earned the nickname the Great Nothing. Spanning over 300 million light-years in diameter, it contains only a handful of galaxies. If the Milky Way had been located inside it, we might have believed we were alone in the universe. The emptiness would have hidden the greater cosmic web from our sight. Supervoids are not just oversized versions of typical voids. They are anomalies, regions so vast and so underdense that they challenge our understanding of cosmic structure. Standard models of the universe predict voids, yes, but supervoids push the boundaries of what should be possible. Their sheer size and extreme emptiness have raised profound questions about how structure formed after the Big Bang, and whether something more exotic might be shaping our cosmos. One of the most famous mysteries associated with a supervoid is the cold spot in the cosmic microwave background, the ancient light left over from the early universe. This region appears colder than it should, based on standard physics. One possible explanation is that light passing through a supervoid lost energy due to gravitational redshift, creating the colder temperature we observe. This hypothesized supervoid, called the Eridanus supervoid, may span over 1 billion light-years across. But the mysteries do not stop there. In 2013, a team of astronomers proposed the existence of an even larger supervoid, the so-called KBC void, named after its discoverers. If real, it could span nearly 3 billion light-years, and it might even surround our own galaxy. Its existence could explain discrepancies in measurements of the universe's expansion rate, offering a cosmic-scale reason for why the Hubble constant appears different depending on how it is measured. Not everyone agrees. The KBC void remains controversial, and independent confirmation is still lacking. Yet even without it, the supervoids we do observe already test the limits of our theories. They are so large that they begin to blur the line between local structure and the fundamental homogeneity of the universe. If the cosmos is supposed to be roughly the same everywhere on large scales, how do we account for such immense regions of emptiness? Cosmological simulations provide part of the answer. These digital models of the universe's growth suggest that, through random chance, supervoids can occur, rare but not impossible. They are statistical outliers, like unusually large waves on the surface of an ocean. But if more are found, or if one turns out to be even larger than predicted, we may need to rethink the basic principles of how structure forms. We may even need to introduce new physics to explain what we see. In the end, it is a quiet irony that the largest structures in the universe are not made of stars, or galaxies, or glowing matter, but of emptiness. The cosmic voids, once dismissed as mistakes in data or forgotten spaces between galaxies, have revealed themselves as the silent architects of the universe. They shape its web, guide its expansion, and hold within them the most ancient truths. To look into a void is not to see nothing. It is to witness the raw foundation of everything. To understand the future of the universe, we must look not only to the galaxies, but to the spaces between them. It is within these dark, vast voids that one of the most profound cosmic forces reveals itself: dark energy. This mysterious entity, first confirmed in the late 1990s, appears to be driving the accelerated expansion of the universe, and nowhere is its influence stronger or more revealing than in the empty regions that surround the cosmic web. Dark energy is not a substance in the traditional sense. It does not clump like matter, and it cannot be touched or directly detected. Instead, it seems to be a property of space itself, a kind of energy intrinsic to the vacuum. When space expands, more dark energy appears, fueling even more expansion in a self-reinforcing cycle. In dense regions like galaxy clusters, gravity holds matter tightly together, pushing back against this expansion. But in the voids, where matter is scarce, there is nothing to resist. Inside a cosmic void, gravity is weak. There are no massive galaxies or thick filaments to counteract the swelling of space. Here, dark energy dominates. It stretches the fabric of the void outward, accelerating its growth faster than in other regions of the universe. This process is not explosive. It is subtle, slow, and relentless. Over time, the voids push against their own walls, thinning the surrounding filaments and drawing matter away from their centers. This makes voids more than just passive gaps in the cosmic web. They are active players in the universe's expansion. Like bubbles in rising dough, they swell with pressure, reshaping the entire structure around them. As they grow, they isolate galaxies, fragment filaments, and hollow out the walls of clusters. The cosmic web becomes more stretched, more fragile, and more disconnected with every passing billion years. It is in this context that the role of dark energy becomes more than a theoretical idea. The voids serve as laboratories where its effects can be observed more clearly than anywhere else. While galaxy clusters are crowded with competing forces, supernova explosions, magnetic fields, and black holes, the voids are quiet. The clean simplicity of their environment allows cosmologists to study the pure expansion of space itself, free from the complex chaos of luminous matter. Simulations of the universe reveal that dark energy became dominant around 5 billion years ago. Since then, the rate of cosmic expansion has been increasing, and the growth of voids has followed suit. What were once quiet basins between galaxies are now the engines of the universe's unfolding. They are not just expanding passively, they are being driven by the vacuum energy that fills all of space. This expansion will only continue to accelerate in the far future. As the filaments fade and the galaxies drift farther apart, the universe will become quieter, darker, and emptier. Clusters will become isolated islands in a sea of void. Superclusters will never fully merge, torn apart by the very emptiness that surrounds them. In time, even the light from distant galaxies will be stretched so thin by expansion that it will vanish from view. And behind it all, the voids will continue their slow conquest of the cosmos. Dark energy is still one of the greatest mysteries in modern physics. Its true nature is unknown, but its effects are real, and nowhere are they more visible than in the deep, quiet hearts of the voids. These regions, once dismissed as mere absences, have become the clearest mirrors of the universe's fate. They show us a future not of fire or collapse, but of silence, an endless expansion into darkness, led by the most powerful force we have ever encountered, hiding in the spaces between. The universe is not static. It is not frozen in time. Every passing moment stretches space itself. Galaxies drift apart. Light weakens. Structures shift. The cosmos we see today is not the same one our ancestors looked upon, and it will not be the same one our distant descendants inherit. To understand the future of the universe, we must look not at what remains still, but at what is steadily moving, at the expansion that defines the fate of all. In the beginning, gravity shaped the cosmos. It gathered matter into stars, galaxies, and clusters. It built the filaments of the cosmic web and defined the walls between voids. But now, a new force dominates: dark energy. It is not loud or violent. It whispers, pulling at the fabric of space itself. Its influence grows stronger where matter is scarce, and so the voids, once passive, now become the front lines of cosmic evolution. As dark energy continues its work, the voids expand. They push outward, driving filaments apart and weakening the bonds between galaxy clusters. The cosmic web, once tightly laced across space, begins to fray. The superclusters will never fully merge. Instead, they will be torn apart, their galaxies scattered. Over billions of years, the universe will shift from a web to a sea, an ocean of emptiness with isolated islands of light. This process is not fast, but it is final. The galaxies will continue to form stars, but even that will slow down. Hydrogen will run low. The brilliant, hot stars of today will give way to colder, redder, dimmer ones. One by one, galaxies will darken. Black holes will linger, but even they will eventually fade. And as the stars wink out, the voids will only grow larger, claiming more space in the silence. In the far future, the universe will be nearly empty. Light from distant galaxies will be so stretched by expansion that it becomes undetectable. Cosmic background radiation, once the warm afterglow of the Big Bang, will fade into invisibility. All reference points will be gone. An observer, floating in some distant galaxy, may believe they are alone, surrounded by darkness, unaware that a vast universe once existed. But the story does not end in fear or despair. It ends in understanding. The growth of the voids tells us what kind of universe we live in. It tells us that expansion is not a moment, but a destiny. And it reminds us that emptiness is not meaningless. It is the stage on which all things unfold, the silent rhythm that shapes the final chapter of the cosmos. In a universe filled with noise and light, it is the quiet places that hold the deepest truths. While galaxies blaze with stars and black holes roar with energy, the voids remain silent, untouched, undisturbed. And in that silence lies clarity. Cosmic voids are not just vast expanses of emptiness. They are time capsules. They preserve the original conditions of the cosmos better than any star or galaxy ever could. They are the still surface of a deep well, reflecting the earliest moments of everything we know. Galaxies are turbulent. They collide, they burn, they explode. Over billions of years, their histories become chaotic, their structures overwritten by gravity, radiation, and motion. Trying to understand the early universe by looking at galaxies is like reading a book with half the pages rewritten. But the voids, vast and quiet, have changed little. They have grown, yes, but they have not been stirred. Their shape, their density, their smoothness, all retain the fingerprints of the infant universe. This simplicity makes voids ideal laboratories for cosmologists. The physics is clean. The dynamics are slow. Inside a void, light moves undisturbed, and matter is too sparse to create complications. When scientists simulate the early universe, they test their models, not only against the bright structures, but against the darkness as well. If a model fails to predict the size and shape of voids, it cannot be complete. To understand the full story, the silence must agree with the sound. Voids are also uniquely sensitive to the ingredients of the cosmos. The amount of normal matter, dark matter, and dark energy all influence how voids grow. If the early universe had slightly different proportions, the voids would look different today. In this way, voids become diagnostic tools, delicate tracers of the cosmic recipe. By studying them, we can reconstruct what the universe was made of when it was still young and how it has evolved over billions of years. There is a strange beauty in the idea that emptiness can carry so much meaning, that by staring into the deepest darkness, we may glimpse the purest light of the beginning. Voids are not merely the leftovers of cosmic growth. They are the untouched canvas, the raw backdrop against which all things have unfolded. They whisper of a time before galaxies, before stars, before even atoms. A time when the universe was quiet, simple, and full of potential. In the end, it is a quiet irony that the largest structures in the universe are not made of stars, or galaxies, or glowing matter, but of emptiness. The cosmic voids, once dismissed as mistakes in data or forgotten spaces between galaxies, have revealed themselves as the silent architects of the universe. They shape its web, guide its expansion, and hold within them the most ancient truths. To look into a void is not to see nothing. It is to witness the raw foundation of everything. We often search for meaning in the luminous, the bright spirals of galaxies, the fires of stars, the violent drama of black holes. But the story of the cosmos is just as much written in what is missing. The voids are where space expands, where dark energy reigns, and where the history of the universe remains preserved in clarity. They are the cosmic background, the negative space, the silent partner to creation. They do not shine, but they shape all that does. As we map more of the universe, and as our instruments grow more powerful, we are learning to listen to the silence more carefully. It turns out that the voids are not empty at all, not in meaning, nor in significance. They are the universe whispering its secrets. And in that whisper, we hear the echo of the beginning, the rhythm of its growth, and the shape of its fate. Sometimes, to see the universe clearly, we must look not at what fills it, but at what it leaves behind. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.